I'm very happy to have Andreas today. He's going to tell us about periodic Dilaton gravity.
Hey, thanks, Sophie, and thank you all for coming. I'll be talking about, well, some work with a bunch of people. Adam, who is here today, and Thomas and Jacopo from Ghent, and Klaas from Colombia. Klaas has been here a few times for a day, so maybe you've seen him around. So we had a paper in April, and then a couple of papers that should come out relatively soon. I'm mostly going to talk today about the stuff that's going to come out. Okay, so it's just some general background or whatever. Suppose we would consider a 2D Dilaton gravity with a periodic potential. I want to advocate that these are sort of funny models, and no, I think they're all right. One way to appreciate it is that the models have a bounded ADM energy spectrum. Therefore, in a sense, there would be natural candidates as toy models for the quote-unquote UV complete model of quantum gravity, simply because there's an upper bound and lower bound. And well, regardless of what I'm going to say, one could be interested in the effects of this periodicity on quantization. But I have a somewhat different motivation to have started studying that. But today we'll focus mostly on sine Dilaton gravity, even though I quite strongly believe that the physical conclusions we're going to reach should be universal for these other models, which I think is something that we would like to make more precise in the future, but it's hard to see where it would really go wrong. But this model is especially interesting for several reasons. Well, the first two are obvious. It's first of all the simplest example of the periodic potential. The second is that this theory turns out to be exactly solvable, meaning, as I'll show you, we can quantize it various ways and get precise amplitudes out of it. But maybe the third and the fourth reason are more important. So the sine gravity theory we've shown is an exact hologram of a known microscopic theory called double-scaled SYK. And well, that's good. If you have an exact holographic relation with the quantum mechanical theory, you can hope to use input from that hologram to try to learn the rules of gravity instead of putting them in. So that's sort of the logic that I want to follow here. As I want to take something that the holographic theory is telling me I should do and draw lessons from that. And I feel like these lessons will generalize to more general potentials. I don't want it to be something very specific of sine gravity. I want it to be general.
Would you say rather than the exact hologram, it's just the exactly correct holographic related to a sector of this double-scaled SYK? Yeah.
Okay.
Because it's just the Hamiltonian insertions, right? Not the other.
Well, we can compute correlation functions, but
those are fields that are not included in this theory.
No, we can compute correlation functions of double-scaled SYK in this theory. But okay, they're not. Yeah, we probe matter part. So they're not inherent to the theory.
Right. It's like the Schwarzian, the analog of Schwarzian.
Yeah, precisely. So it's like not pure JT, but JT with particles.
Right.
Precisely.
Thanks for the citation. As for my surname has the H and the L interchange.
Yeah, but I already put the UE after you complained last time, so I made the comments. Last time I just put U as you complained that I didn't put the umlaut. I said we don't do umlauts, but okay, slowly I'll get it. It may be wrong in many places.
Yeah, I saw him.
Please prepare.
That person.
Okay, so this is another motivation is that this theory has a cosmological interpretation, and I'll give some comments on a 2D cosmological interpretation at the end of the talk. The 3D stuff many people here have done. It's not my work, so I'm not going to discuss it. But I feel like the overarching idea or motivation for me is to use this SYK model to learn new rules of gravity that hopefully have a good impact on quantum cosmology. What that good impact means, I'm not precisely sure, but I feel like well, at the end of the talk, there's some comments that I feel are trending in the right direction. You can judge for yourself. Final motivation is again something that I'm not really going to discuss, but this model can be rewritten as two Liouville CFTs, and yeah, there's been remarkable progress on this by Beatrix and collaborators in solving that theory. They don't do precisely the same as what we do, but it's still the same theory. They just treat it differently. And this is more like an argument to say, like, there's clearly a ton of interesting structure in this model. And regardless of any motivation, if there's a theory which is exactly solvable to a high degree and so many nice things appear, it's, I feel, always worth investigating in more detail.
Question. There are many fonts with phi. Can you go through all of them?
Phis.
So there's uppercase phi in the box,
Yeah, uppercase phi is the dilaton.
and then that's periodic.
That's the one with the periodic
And the
potential.
one that appeared on the previous slide, is it the same font or no? This
That's the
one?
same font.
This, is it invariant if we shift phi by 2 pi?
Yeah, the R is a bit of an issue, but it's not an issue on the topologies I will discuss today. But the potential is periodic.
So you cannot strictly identify phi with phi.
Well, you can if you work on specific topologies. If you cannot,
Like on a torus or any
That topologies.
yeah, essentially. So the disk works, but it will become clear at the end why the disk works. And then
Which
the torus.
topologies are okay?
Like if the ridge is zero.
Sorry?
If the ridge is zero, like.
So it's not just topology.
If they're close, it's the other right.
Okay, I think we should discuss this at the end of the talk. I think it's interesting, but yeah, we can see where we get, and then I will focus on disks and cylinders today.
or instead you would write it as some more difference of two Liouville actions, then the issue kind of goes away.
Yeah, if you do integration by parts, then it's in some sense, as you say, it doesn't look like that. But still, if you do Liouville, you still have the curvature of the background metric. And you cannot, for a general topology, you cannot go to a background metric, I think, where this R is zero everywhere.
Why do you say this Herman and it disappears?
Because R is not literally there.
Yeah, because then you need to partially integrate the dispersion.
But the issue is not only that, I is really circle value. And it could wind around non-contractible cycles. And then the action is not well defined.
Right.
So integration by parts is not going to.
Yeah, not much to say about that.
Still say that if it were true, happened to be true that the action appears in the exponent such that your shifts are quantized with multiples by I, then it's a bit like a transimus action.
So there's no I there in the first term. In the
Understand.
previous signature, there's no I in front of the phi R.
There are going to be I's in the story then.
But if you put an I there, there would be also an I in front in the sign.
I think these questions will become probably still.
Okay, proceeding with let's just see where we get. Sometimes I think it's better to follow the nose and see what comes out, but these are significant things. I don't quite know how to treat this theory on more general topologies. But, anyway, I'm not too interested in that for the moment. Okay, so as I said, we'll be interested in treating the shift symmetry as a redundancy. And yeah, this gauging was originally inspired by double-scaled SYK. Okay, as a motivation, but on hindsight, it actually seems necessary to make the theory well-defined, as you'll see from the equation that follow. Okay, so before giving an overview of the talk, let me briefly present the classical solutions of sine dilaton gravity, where the dilaton is the radial coordinate r, and the metric takes this form. The relevant holographic integration contour is the following. It's in a complex R-plane. It looks a bit funny, but it looks more natural once you do a Weyl transformation. And in fact, a lot of the features in this, gravitational features in this model are more intuitive when you work with a well-rescaled geometry or well-rescaled metric. Replace ds squared by ds squared e to the minus I phi, which is a Dilaton still. You find that this metric becomes simply an ADS2 metric, and this funny looking contour I draw is the ordinary real row contour in the ADS metric. The hologram lives here. Yeah, the ordinary ADS bar in some sense.
So you're taking out to be machinery.
Yeah, this is the complex R plane. So I start at real R, but then I go up. This corresponds with the real row.
So we're in Euclidean ADS?
Yeah, we're in Euclidean. But tau is not affected, so I can always recruit it tau.
I don't understand why you introduced eyes if we want to be in Euclidean, we have a real Euclidean.
You mean here?
Yes,
Okay.
the right hand side. Yeah. Oh, sorry.
Oh, but the R contour is not real.
I see.
So
I see. So the metric is not real. It's e to the minus I5 that's real. If I change it.
well, it's a metric times e to the minus I phi, that's real. So neither phi nor the metric are real. The combination is.
What is that? What is that?
Theta is yeah, I didn't say that, thanks. Theta is the value, is the horizon value of the dilaton. So f of r vanishes when r equals theta. Since phi is r, this means that phi at the horizon is theta. So theta is a parameter of the solutions, labeling the area of the black hole or its energy. Okay, so now some take-home messages and structure of the talk. So generally, and perhaps unsurprisingly, periodically identifying a dilaton will end up discretizing the length of Cauchy slices. But okay, there's several consequences of that. For open Cauchy slices, become clear what I mean precisely. Okay, the length becomes discretized and you find many null states. And this turns out to drastically reduce the entropy such that it's much lower than the naive black hole entropy. That statement will become clear. It's an overview. Second, for closed Cauchy slices, it will become clear that the length of the trumpet becomes discrete. And the consequence of that is that the physical Hilbert space reproduces spectral correlations that are universal of the single cut matrix integral, which leads us to believe that our model is actually a path integral formulation of what Jeffers and company called the q-deformed JT gravity. And they took a matrix integral definition. And third is the comments on cosmology, is that the usual Dirichlet-Neumann non-binary state in this theory is actually not physical. Instead, what happens is that the disk is a coherent non-binary state with support on discrete trumpet lengths, and is therefore normalizable as coherent states typically are. Okay, let's start with the open slices. So the question is, what is a canonical quantization of sine Dilaton gravity on a global time slice? This is the part of the talk that's review of the paper that we had in April. Talked about in several places, so maybe you know about this already. I'm gonna find it convenient to consider a length variable that is an effective ADS geodesic length variable. So I'm computing the length in this Weiler-Scaled metric. The classical saddles of this would be geodesics in the effective ADS geometry. And okay, solutions are the ordinary ADS solutions, just with the sign.
Can you remind us every character here, which one is real, which is imaginary?
L is real. Everything that's effective ADS is real. So neither ds is real nor phi is real. The combination is real. L is real. As this, indeed, this.
So can you change variables such that the eyes are in one place?
Well, essentially, I'm choosing this as new metric in some sense, which is real. Is that what you, well, I could choose, of course, a real contour for the original metric, but then it doesn't go to the holographic boundary, so.
So when I look at right hand side equation in the box.
Yeah.
Theta, rho, and tau, are they all real?
Yeah, they're all real.
I understand why, because I thought the sine dilaton theory does have a completely real Euclidean ADS solution. So
Yes, it does, but
why is that not?
it's this one. But I don't want to do that because I want to go to this asymptotic boundary. And I want to do that because that is what the SYK model is telling me to do.
I mean, that solution has those real solutions, they don't have a boundary. I think they're more like cosmological solutions. They look like bubble negation solutions in some way.
Well, it's a short.
Yeah, it's or the Sitter-Schwarz.
I thought the sine has infinite many critical ones, and I thought half of them give anti-Sitter solutions.
Look. That's correct there is one solution like that where phi that takes a very specific value
Oh, I see. But
and it's constant, so it's not the usual.
I see.
He's considering the different solutions.
Is the action in your contour isn't bounded from the old shot?
The phi r plus sine phi.
Yeah.
Oh. I don't know.
Because if phi is real, it seems to me that it's not in Euclidean symmetry.
Well, you could do the same for JT then, no? Phi times r is there also. Phi is real. Takes values on all axes.
So the rho here is just,
I thought that there what you do, you use phi as a branch multiplier.
Yeah, true, but nonetheless, the solutions you consider have real
Which
phi.
really means that you don't think of phi being on the real axis.
Well, you can say that, nonetheless, the actual solutions have real dilaton. So there seems to be some tension between what the solutions are and the integration of the people typically use, but the solutions of JT gravity most definitely have real dilaton. So I'm not answering your confusion, I'm just saying it's the same confusion as in JT. So, and that theory seems to work pretty well, I think. I mean, there's a sense in which phi can be treated as a Lagrange multiplier here too. But that takes another type of explanation. Well, takes us a bit further. You can write the gravity in first order variables, and then you have a dilaton and two other fields which you can actually integrate out. Then you would, I guess, consider that.
There's a big difference that you rotate the contour such that phi is imaginary, and the sine might be problem. I there
Yeah.
comes pi times hyperbolic sine.
All right. Yeah, I haven't thought about that.
maybe with cosine it would be okay. And you get the Cauchy, but. So what's a rho as a function of r?
Rho as a function of r. Well, I mean, I can write it down half and half the sum log.
So it's just the length along the blue line, right? The rho.
Well, it's not precisely the length.
But you want to keep
Yes.
the rho
Yes.
to be real value along the blue line, right?
Yeah, precisely. Well, the coordination transformation, you can work it out, just multiply it with e to the IR and find the relevant transformation that brings r squared over f of r e to the minus r in the form 0 squared. So it involves some log and some i's.
You can take any method and choose a complex one, some current transformation, type of transformation to get it to radius.
Probably yes. Well,
Risking.
Yeah, I think you can probably take any metric and value scale it to. Yeah. So we,
Yeah. You said this is a geodesic, is it a geodesic in the ADS metric or in?
the ADS metric, because the action is this, so we have variation. Variation of the trajectory gives.
So the motivation considered this effective length is just because it's oh,
The motivation is that the motivation originally comes from again double scaled SYK, because this is the expectation value of e to the minus delta times this length computes correlation functions in the theory. And
why in the correlation area the E2I5?
sorry, what?
Why in the correlation function there is E2I minus I5 over 2?
We don't get to choose that. No, there's a holographic theory which has certain correlation functions, and we have to find which one of the observables corresponds with it. And in this case, it turns out to be that it's these non-minimally coupled particles. Like this may be funny, but it's nevertheless a fact. So yeah. But going to this variable has nice, well, nice consequences though, because it actually allows for a quite simple canonical quantization of the theory. And yeah, in that sense, you know, there may be a way to do this for general dilaton gravities, because as one asked, you can always sort of well rescale to ADS, and then some of the confusions you have in a general background about what are geodesics, etc., go away. Anyway, so the phase space of sine dilaton gravity is two-dimensional, and labeled by initial conditions as always. One variable is the horizon radius, and the other variable is a two-sided time. So this two-sided global time evolution. The ADM energy in this theory is labeled by minus cosine theta, which you read off from the shell action. And the symplectic form takes this form. So we can ask what is this P conjugate to L, and we can compute that because we have an equation for L. We define this Hamiltonian. So now we can quantize that Hamiltonian by solving its Schrödinger equation. So if you look at this, you can find solutions which, even though they're quite complicated, they're explicit, like something like this.
Be bothered by the fact that Hamiltonian doesn't look permission.
Not really, no. There's a version of the Hamiltonian. You can do some transformation in phase space where you shift P by an imaginary constant to make it look real, and work with that. The answers are the same. Also, like we always work with this non-Hermitian Hamiltonian. The non-Hermitian Hamiltonians are not necessarily bad. It just implies that the left eigenvectors and right eigenvectors of the Hamiltonian don't have the same functional form, but they're nonetheless orthogonal. So you can work with non-Hermitian Hamiltonians in certain circumstances. This is one of the cases for.
Are you saying it's conjugate to a Hermitian Hamiltonian?
Yeah.
This non-Hermitian Hamiltonian PT symmetry.
What does that mean? I don't know.
Some symmetry that implies that the eigenvalues are.
Yeah. Like in quantum mechanics, people have been writing a lot of papers about PTs. I can imagine.
Complex conjugate is equivalent to itself up to a symmetry, which may be with the P going to.
Probably what your first statement implied.
This is just saying that this Hermitian will be different in approach, right?
And because P and L are not commute, right? And how do you assign the order of the P and L in the second term?
Yeah, okay, there's ordering ambiguities as always. We choose a specific ordering that gives some quantization. That's always the case, of course.
Yeah, and then why do you choose this one?
Because it gives nice answers.
Okay.
Okay, so these are the wave functions. Well, you don't have to remember that. What you maybe want to remember is that they satisfy the following orthogonality relation. And from that one reads off the density of states. this results in the following partition function for the gravitational system. Now, this doesn't look like a particularly nice partition function. It's actually divergent because of the periodicity of the energy. So if I shift theta, okay, this term remains the same, but this is not so. I just have an infinite order of things that I sum, and it's bad.
Let's change the sign, the argument, yeah. Then. So, yeah, so we cannot should we interpret again this product of the sign?
No, I would probably call d theta sine theta the energy and consider this a real spectral density.
And
That's a bit subtle here because it's multi-valued.
and also because the integral goes over a range.
Yeah, so the spectral density at fixed energy would be like the infinite sum of the copies of the sinh, which is divergent. Okay, but this issue can be resolved by treating phi 2 phi plus 2 phi as the redundancy, which I'll discuss next. Yeah, there's something here that confuses me with what Beatrix and friends do. Well, it's interesting, but also confusing to me. They consider the dilaton at the horizon to be imaginary, and then this makes the integral convergent. As far as I understand, I find this a bit confusing because it's like considering imaginary black hole areas, but it's a nice answer, so it's interesting. I'd like to better understand where it comes from. Okay, sorry.
Sorry, I just had one. On their result, they're not doing this redundancy identification that you are doing.
Yeah, because they, like I said, they consider the dilaton on the imaginary axis, so then it's not really a symmetry.
This is related to the question I asked before. What exactly do you mean by treating it as redundancy?
Well,
For every position in space, time map to phi circle value, is that what you mean?
well, I think it will become clear from what I will say, what I precisely mean. Okay, so for open slices, actually what I mean is this. It just means that the Hamiltonian is invariant under momentum shifts. And it's this symmetry that I will be gauging for open slices. For closed slices, it'll be somewhat different, but we'll come to that. But I want to emphasize that this, even though I'm not at this point immediately gauging this phi shift symmetry, it is a direct consequence of the periodicity of the potential. So like for any potential, you can more or less show that if the potential is periodic, then the momentum will be periodic with the same period. So the Hamiltonian you get will always have the required symmetry, and I'm imagining for generic periodic dilaton gravity to gauge that symmetry. So we'll do that now.
Sorry to interrupt, but P was the quantity canonically conjugate to L.
Yes.
It's going to be to what?
L.
So L is naturally going to be quantized.
Precisely.
Wait, but the P has the shift, doesn't that mean L has redundancy?
Yes, that's
What's the relation between L and phi? Yeah,
L is not quite related with phi. It's more P is more closely related to phi.
but L is untraceable.
Yeah, so P will become periodic and L will become discrete.
Oh, okay. Oh, okay, yeah, sorry.
Like the opposite of what we usually. Usually we take X to be periodic and P becomes
Yeah.
It's just the other way.
Does P have a clear geometric meaning or?
Half and half, so not very clear, I think. I would say it's the tension of a certain brane in the theory. Just because it's like you do the on-shell action and you do like the on-shell action DDL, that gives P. By definition of what it means to be a complex conjugate. So you can view P as the tension of a slice in some sense. But it's not simply the time derivative of the length, because the Hamiltonian is not P squared. So it's not.
Is P circle valued or just a symmetry?
Yeah, I want to take P circle valued. Because initially it was not, but now I want to take a circle values. Initially it was a symmetry, but I just took the symmetry as it was. Now I want to put it on the circle.
And phi you have to check, because you say it's a symmetry of phi.
What?
Phi, should you treat phi and 5 plus 2 pi as the same point or not? Because you say there's a symmetry.
Yeah, I wanna, morally, I wanna also, put phi on the circle.
But for example, your formula wasn't invariant when you're shifting theta by 2 pi. If we go back to the last page,
Yeah, that's true, but,
and theta was the value, horizon value of phi. like you said. So it looks like there isn't a symmetry of shifting theta by 2 pi.
okay, but there is a symmetry in the shifting p by 2 pi. So let's just deal with that and see where we get. Okay, so I want to gauge the shift symmetry of the momentum now. It's probably less confusing to you all than me saying I gauge a dilaton. So, okay, what we do is we construct projector operators as always that project on invariant states. There's the infinite normalization factor, which is funny but important, and it's determined by the fact that the projector is project. So we construct invariant states. In this space, you will get null states, which have to be modded out to get a physical Hilbert space, and I want to now sort of manually construct that physical Hilbert space. Okay, so to do that, I want to compute the inner product between the projected data eigenstates. Just to find out what the new inner product is. From an inner product, I read off their completeness relation, etc.
Can you clarify this formula or the one on the previous slide?
Which formula?
So how should we think of this pi?
As an operator that projects on invariant states.
Such that L is an integer.
Yeah, but L is conjugate to P, so this generates shift in P plus 2 pi. But yes, yeah, indeed, obviously it means that L is an integer because I can rewrite it as a Dilaton essentially. Yeah. So if I let this act on a P state, e to the 2 pi IML shifts P to P plus 2 pi M. That makes
Which
it.
has quantized as usually we do for periodic variable.
What?
I mean, usually when we have a variable that lives in a circle, which is a descending integer.
Yeah, but it comes down to that. I just want to do it a bit more from. I wanted to emphasize here the relation with what you do in the original theory, which has a symmetry, but I don't gauge, and now I want to, work sort of manually by putting in operators. So I think something quite remarkable happens here to the wave functions at the discrete points. So which plays well with this infinite normalization factor. Namely, it turns out that these wave functions develop like divergences at integers, and they precisely cancel with this infinity and give a finite sum over n here.
Why you have the null state? I mean, you just kind of quantize the basis for the Hilbert space, integer L, right? And you are saying those bases, there are some redundancy.
Yeah, so if I put L equals to 1.357, this is a null state.
Well, but that have been projected out.
Okay, but there
So
are null states in
and
the
also what I'm confused is like you already project out and saying the project out space. After projection, there's still some null state inside the Hilbert space.
Yeah, let's discuss this in the next slide.
Oh, okay.
Okay, so because of these divergences, like I said, this combination remains finite and it sort of only reduces to a combination of wave functions, which we know very well from the SYK system. And actually, crucially, this combination vanishes for negative integers, which I don't think is very trivial, but you can sort of see it from this plot. There's no peaks here. So whereas this guy with projects on all integer ends, actually in the theory, states with negative n are not null states. They don't have they don't contribute. This maybe in part answers your question.
Okay.
In the databases, it works slightly different, as I'll show now. Okay, it's a side comment which I'm going to skip.
Is L the length?
Yeah, okay, so I'll not skip the side comment. L is a renormalized ADS geodesic length. Because I introduced the DL e to the minus I phi is DS ADS. So it's a length in an ADS metric. But since we go to the actual holographic boundary in ADS, the physical length is still infinite, so we have to renormalize it in the usual way to get the finite thing. So L is a renormalized length. Therefore, negative L is not a priori unphysical. And in fact, for instance, in JT and other Dilaton gravities, negative L is very important and contributes tremendously to the partition function. So this is a highly non-trivial constraint. Okay, and now the redundancies and the theta bases. So using the identities that I showed, you get the following inner product between the projected states. Find this. I mean, I threw away some prefactors, but for the purpose of the talk. So you see that they're actually over complete sets because states that correspond with shifting theta to theta plus 2 pi are actually identical. So what this means is that we should mod out by these states, and this gives us a completeness relation in the gauge theory. The fact that the partition function did not seem periodic in shifts in theta has to do with the prefactors that I sort of ignored here. But this equation is still morally true. Okay, and like I said, in the length basis, this becomes the physical identity. So we found, unsurprisingly, that gauging the momentum discretizes the length, but surprisingly, negative length states are null, so they don't exist. And this has a huge effect on the entropy. Indeed, if we compare the naive gravity disk calculation, it was this guy as or maybe more distinct as density of states. Whereas if we compute the gauge disk, get this new expression for the density of states. And one sees as a consequence that gauging reduces the entropy tremendously because the entropy of the black hole, which is like this pi times theta over 2 log q, which goes linearly. Upon gauging the momentum, it falls down to this quadratic curve. So in other words, the entropy of the gauge theory is much lower than the black hole area. And this arises because of the many null states. As such, I think it's a similar flavor to the information paradox. Okay, this ends my discussion of open slices, and now I'll turn to closed Cauchy slices. So our remaining goals are the following. I want to, in an appropriate sense.
Before you start this,
Yes,
so
sir.
that previous formula, that's the same as the one they had?
This one?
Yeah.
Still not quite, because they consider theta to be I times x.
Talking about
I think
the
so, yes.
chord diagram.
Oh.
By Vladimir and company.
Oh, okay. This is the same. This is the same as what they had. That's what Vladimir and friends.
Okay, fine.
This is this quote unquote naive thing you would get from Dilaton gravity. So it's e to the 2 pi Dilaton in an appropriate sense. Minus e to the minus 2 pi Dilaton. Okay, so now I'll show that in an appropriate sense, which will become clear that gauging the shift symmetry in phi discretizes the length of closed geodesics. And I want to compute the double trumpet and describe this Korean Novartis implementation. Yeah, so we'll start with computing the trumpet at finite cutoff in sine Dilaton gravity, where this B parameter will label the effective next circumference of the trumpet in again in the ADS metric. So again, this is a real parameter. So there's two independent ways to compute this. One is via radial Wheeler-Witt quantization, and by radial I mean you go in this slice and you use closed Cauchy slices. Another is via end of the world braids and inverse Laplace transforming them. This is a quantization in the open channel, so I quantize the slice like this and then compute the partition function. Give the same answer. So first I'll discuss briefly the Wheeler-Witt quantization. And for that, it's convenient to introduce two effective ADS metrics. The one that we had before and well, a brother of it, which I label ds squared ADS bar, where I put the opposite sign for the dilaton here. Now in the Liouville language, yeah, okay, obviously no, it's not applied. In the Liouville language, these are just the ordinary Liouville metrics for the two fields, so quite natural variables. And associated with them, I now introduced three length variables, which I realize is becoming a bit much of notation, but it's actually very helpful to organize the math. So L is the variable in the ADS metric, L bar is the variable in the ADS bar metric, and then I have just the ordinary L in the sine Dilaton metric. And only this guy is real. So the ADS bar metric will be will take a complex contour in the ADS metric. Okay, and also I will introduce extrinsic curvatures for the Cauchy slices, both in the ADS metric and ADS bar metric. This is convenient because the Wheeler-Witt Hamiltonian in these variables looks very simple. So I work in mini superspace. So when I say identify the dilaton, I mean it in this mini superspace language. So the phase space, okay, the symplectic form on phase space takes the following form in these variables, and the Wheeler-Witt Hamiltonian is this. This is a nice form of the Hamiltonian because it sort of factorizes between the two pairs. So I can solve for the eigenfunctions of this equation just by separation of variables. Again, there's some operator ordering ambiguity here, but okay, there's ways from the CFT formulation to understand that this is the appropriate ordering. Funny enough, and typically in Dilaton gravity, people use a slightly different ordering, but okay, there's no semiclassical effect, but the wave function looks slightly different.
So the phase space is 4-dimensional?
4-dimensional. Then I will constrain it and gauge one so it becomes 2-dimensional. As such, the eigenvalues of this equation B, they will label the physical Hilbert space. Because as Juan said, the phase space is 4D, but the Wheeler-Witt equation eliminates 1 degree of freedom. That means suppose we eliminate K bar, then L bar has no symplectic form, so we can gauge that to whatever value we want. And then you have just a 2D phase space remaining, which means that your physical states will be labeled by one parameter. This parameter in this case is the length of the trumpet.
Is the mini superspace approximation exact here, or can you have other variables? I would assume it's the exact name.
Yeah, I don't know actually. It might be exact, but I'm slightly confused.
Yeah, it's a choice of gauge, no? That teaches the.
Yeah, that's what I thought.
Yeah, if you guys understand this better, then I'll be happy to. I was slightly confused in the string language about descendants because B would label primaries. Anyway. Okay, so the solutions of this equation are the finite cutoff trumpets. So they're a product of two Bessel functions, well, a Bessel and a Henkel. Okay, so we found the physical states that solve this constraint and their wave functions. So a few comments, and when I take the holographic limit for the whole scale SYK, which is this choice of parameters, the wave function becomes just an ordinary Bessel I. the ankle becomes a face, but that's stripped off by some sort of by usual counter term, holographic boundary. The second comment, which I've already said, is that B is the length of the neck, and it's or simply is a parameter labeling the physical states. One way to appreciate that it's the length of the neck is this equation, where if I go to a geodesic, this really just says that B equal to L. Okay, I think I will skip this in lieu of time.
So are those two variables that you had before same as the two variables that the complex discussion had?
Right. Yeah, because this is a Liouville field and other Liouville fields.
Okay.
So this is actually a nice language to quantize. But it's sort of obvious because in the Liouville fields, the Liouville actions decouple, so therefore the Liouville with Hamiltonian, etc. and the spectral formats will also tell.
Are you identifying B and L only after you do the quantization, since you just said before that you get L is only positive definite after you do the gauging? So this is all doing this after the gauging, right?
This is a prior to gauging.
This is prior, but then you were saying before that L, the way you were defining L, it could be negative infinity. Like B is a finite quantity here, and how can B?
Okay, sorry that this is not very clear, but now I've switched to closed slices. And for closed slices, I do not have to do a holographic representation. So in this case, L is actually the length of the slice. So it is already positive.
Phi at the moment is not yet periodic.
No, it's not. But it will be.
I just missed so what, like, why is the phase space different than JT? Like, why is it 4-dimensional or 2-dimensional?
It's not, it's actually the same. In JT, it's 4-dimensional prior to imposing a constraint. Just like if I do finite cut of JT, I would also fix the dilaton and the length, for instance.
Yeah.
But still, if I take an inner product on slices, I only do one integral instead of two integrals. That is because there's a Wheeler-DeWitt constraint that eliminates one of the two variables roughly. So it's exactly the same as in the JT story. Yeah, in fact, the JT story is a suitable limit of this. Remains a suitable limit. Okay. A low energy limit. Okay, so I'm gonna skip this, but there's another way to compute this trumpet using end of the world brains and quantizing that. Okay, which is quite a fun story, but yeah, I mean, time is limited. Okay, so now I want to discuss the effect of the gauging of the dilaton on the state spectrum. And this is simple to appreciate in the small length limit of the wave functions. If you take these this Bessel J and Bessel and angle function for small l, it reduces to an ordinary plane wave. Now I see that if I identify the dilaton with 2 pi, this means that the B has to be discretized for the wave function to be physical. In other words, these states are eigenstates of the conjugate to the dilaton, which is B, which therefore needs to be discretized.
So here you directly impose the gauging phi equal to phi plus 2, but not just B. The gauging don't have 2 pi P.
Precisely.
Okay.
So it's slightly, yeah, in the closed channel, it's slightly more clear. Okay, so we have wave functions, we have physical states, and now I want to compute the norm on those states. For 2 reasons. First, because, well, a little space of closed universes, I think it's kind of interesting. I mean, not everyone maybe, but I think, and it's not so often studied. And second is that you need it to compute the double trumpet, which I want to do because the wormhole is, except for the disk, by far the most interesting topology in gravity. So I want to understand what it does. Okay, so the inner product is the usual Klein-Gordon inner product inferred from the Wheeler-DeWitt Hamiltonian. So it's useful for this discussion to rewrite the Wheeler-DeWitt Hamiltonian in terms of the sine dilaton length and the dilaton variable. So I do a transformation from the Liouville variables. And it will be simple because of this form of the wave function to compute the inner product in the L to 0 limit. So this is a null slice, and the Pythagorean inner product on that slice takes this form. Okay, and so if you compute that, because they're just plane waves, it's a very simple computation. You get this inner product, B1, B2 is delta B1, B2 or B1. I think actually that Henry Maxfield did a similar type of calculation for JT a few days ago in a paper, but I didn't look at it enough yet. Well, it sounded related. But that was for JT, this is sine Dilaton. So then we can compute a double trumpet simply by inserting the identity in the spaces. And what you get is the sum over Bessel functions in the asymptotic limit, which is an equation that is familiar if you thought about finite cut matrix integrals at some point. In particular, it results in the following spectral correlation, which may or may not look familiar to you with this variable for the energy. But as I said, it's an exact universal leading order spectral correlation in a single cut matrix integral, which by no means had to happen. Like obviously not all gravity theories are matrix integrals. And I don't know if this is a matrix integral because I don't understand higher topologies yet. But at least the spectral correlation, which is the most important, well, which is basically the raison d'etre of matrix integrals, is what you expect.
Sorry, can we go back to the previous slide? Does this come from, I mean, naively we have expected the workout to be just E minus E prime, or E1 minus E2 squared, maybe up some measure factor in the top because
This is E1.
maybe a sine, I would have expected a sine of theta 1, sine of theta 2 in the numerator.
Yeah, but that's just because so this happens because I do like d theta 1, d theta 2.
Yeah.
If I would write energy 1, energy 2, I have to transform this because it's a density, and then you get the signs. Does that make sense? Like, this is a density that I'm supposed to integrate with d theta 1, d theta.
Yes, I understand that. So the difference between the ones in D and the other ones should be a factor, the derivative of the theta.
Yeah, so this is d theta 1 times sine of theta 1.
So I would have expected, maybe this true for some trigonometric identities that product of cosines.
This product of cosines here is it's actually, well, that's a usual expression, at least that I found, that people write it like squared energy 1, squared energy 2. No, energy 1, energy 2. Divided by.
Just okay, maybe I'll ask that.
And it's 1 divided by the sine.
Okay, now I think I understand.
This comes from this putting the sine in. Okay, so this result suggests that our theory is a path integral formulation of what the Jeffers and friends called the q-deformed JT. Okay, so now briefly some comments on 2D cosmology. So recall that with the DSSYK holographic boundary conditions, I chose the following metric contour, which is kind of funny, but okay, we don't get to choose how the holographic duality works. And the effective metric along this contour was the following. But now I've already solved the theory at finite cutoff anyway, so no one is now telling me anymore what the boundary conditions to put are. What I will keep in the theory is the lessons that double scale SYK gave me, namely, I should consider discrete lengths or periodic dilaton or whatever. That I want to keep, but and now I'm just allowing for more general boundary conditions. I'm taking the gravity theory as is. And so in particular, I'll be interested in a more cosmological interpretation of the physical states that I found. So these physical states are trumpet metrics, and a trumpet has has actually a horizon at an imaginary location in the metric plane. So it will be convenient for this interpretation to consider the following metric contour. So where I start at this imaginary value of the horizon, and I just go straight up in our plane. So if you look at the metric along this contour, this is simply a Big Bang cosmology. It's a DS, well, pure de Sitter space. Indeed, it's known very well that like a geodesic lengths, if you like switch signature, become certain conical effects. This is notice that this is now a Lorentzian metric, even though I didn't change anything. X is what I used to call tau. If T becomes Lorentzian, T used to be R, but I now consider R on this axis, so it's probably Lorentzian. Okay, but now recall that only integer b were physical states in our theory, so this sort of limits the amount of, well, the spectrum of the Sitter type spacetimes you can have in your universe. In particular, bound spacetimes, which the ones with the neck, they have imaginary b, and so they're not actually physical. The most famous bounds, of course, is the no boundary initial state, which in Dilaton gravity would more or less correspond with a delta function on an imaginary value of b. Okay, it's somewhat obviously normalizable, not normalizable because delta functions are not. Okay, but so what we learn here is that in periodic Dilaton gravity, the naive no boundary state simply doesn't exist because it's not one of the physical states in the theory, because physical states have integer b and not imaginary. So instead, what happens in this theory is that the disk is replaced by the gauge disk, which has this expansion in the Big Bang cosmologies. And then we can ask, what is this wave function on the Big Bang cosmologies? So it turns out that more or less this is actually a coherent no boundary state. So ordinary no boundary states would maybe fix b to 2 pi I or fix k. But this is a coherent combination that has classically the same effect, but looks quantum mechanically obviously very different. In particular, coherent states are Gaussian wave functions, and this leads to textbook normalizable state.
Can you remind me why you take L equal to 0, not just other space or?
Yeah, that's somewhat subtle, so I didn't go over that. So, well, a gravity motivation is the following. The second point that we can think of, like, we want to compute a disk, so that means we want to start from a state that is essentially like nothing. So a way to get nothing, somewhat intuitively, is to consider a brane with infinite tension. If you do that, then in one theory you project on the L is minus infinity state, which is correct. In the other case, you project on the L is 0 state, which is also correct. Because negative n don't exist anymore.
Okay. Okay.
So it like wants to go as low as possible. Yeah, there's another point, but this really falls more from really requires thinking about the Hilbert space with matter and stuff. There's a sense in which in the quantum mechanics that I discussed, this is really the preferred state.
Okay, so L to 0 means like they're just shrink the whole circle.
Yeah. I think actually that was more or less my last slide here.
So in terms of this picture, again, what's the interpretation of L and of?
Oh, okay, maybe this is not the healthiest notation. So this is referring to the open channel. I didn't know how to write this better.
Okay.
I say here also equated slightly sloppy because beta is not really beta anymore. But beta is roughly the length of the circles. The asymptotic boundary.
Right, but then this periodicity of your variable and the discreteness of L, what does that mean in terms of that thing?
Well, in this, yeah, that's less clear to me. Because here I'm thinking more about the closed channel, where I'm thinking about periodicity of B. it is true if I would look in the other channel that also there the length variable would be discretized. But what that means in terms of what the interpretation of that is in this language,
When you say the other channel is, yeah,
the other channel is,
thing that goes around the circle.
yeah, not quite, and more fully, it's just, so if let's just we take a top view of this picture, so it looks like a disc with a puncture in or something. The other channel is that we evolve in this direction. So Cauchy slices are like this. Okay, that's it. Sort of happened time. So a conclusion of the lessons we learned. So the theories with the periodic Dilaton potential have the discrete length of their Cauchy slices. For open slices, we find that there's many null states, and particularly negative n become null states, and this drastically reduces the entropy of black holes, which is semiclassically very surprising. It seems to be a general feature. For closed slices, we in these theories have discrete lengths of the trumpet. The physical Hilbert space reduces spectral correlations reminiscent of a single cut matrix integral, which suggests that our model is a path-integral formulation of q-deformed JT. And finally, in a more cosmological sense, the disk is a coherent non-binary state, not a Dirichlet non-binary state. It's normalizable. This is a kind of satisfactory, I think, because we got this lesson really starting from a microscopic hologram, which led to this normalizable state picture. And so I think it's very evidence to take this gauging, or whatever you want to call it, inspired by double scale SYK seriously. Okay, general mantra, we need holograms to learn the rules of quantum gravity. Thank you.
I have a question about the null state for the negative length. So in the earlier paper in April, you impose a constraint to the path integral by imposing L to be positive, right?
Right.
Okay, here I think it's just replaced by you choose the contour, go to the imaginary like R, such that it's E2 minus I5, but it's going to I the imaginary, then it's equivalent to constraint that L is positive. In other words, if you choose that like a conjugate contour, I will have all positive lengths to be null states, right?
Possibly.
Okay.
I would, yeah. Aside from that, I would reply that in the previous paper, we sort of imposed L bigger than 0.
Yeah.
And then found stuff from that. Here we're imposing that we're imposing this and finding this. So there seem to be like equivalent in some sense. Like
Yeah.
I can start here and find this, or I can start here and find this in some sense.
Okay.
But in the previous paper, I don't think we understood where the discretization came from.
But the second condition is basically about you choose the contour for the path integral for the gravity.
I don't know if that's true. I feel like this is a deeper property of the theory than that. But it might still be true that if you take the other contour, you write different metrics, maybe something else happens.
Andreas, can you go back again to the slide? I think I don't understand this. Like, I don't agree.
Which slide?
What I'm saying, or you saying this is what we are doing, but I don't.
Well, I don't know what, of course, but I'm only guessing.
I don't think that's true.
I think when I look at your density of states, I see this equation. And it's this equation. Well, it corresponds with.
Dilaton, okay, like at this stage, we never did any Dilaton.
Yeah, that's true, but nevertheless, if you give me an action and if you give someone a partition function for sine Dilaton gravity, you can deduce for a Dilaton gravity, you can deduce what they mean by the Dilaton.
But we don't give it. We don't write it down.
Yeah, but you don't have to give it, I can tell you.
Well, it was on our paper, like, you don't,
Yeah.
I mean, we don't know, like, we do not do it, or like. This is not an equation that we wrote down, right, so I don't know, I don't know.
Maybe Andreas should remove the sentence before, because you don't object to the last one.
I think they consider imaginary, yeah.
I don't think so,
Well,
I don't
well,
believe, I
yeah.
don't. We don't have to
I
write
think
it
they
down.
consider imaginary dilaton, but I don't want to say that for them. That would be better indeed.
The conservative savings, it looks, if you took our formula.
It looks
to match it, one would match.
Okay, so.
Also, if you take this, if you consider the saddles of this action, it's the saddles of taking the dilaton at it's a black hole with the horizon at the imaginary value. We cannot, well, I don't think. I think that is a fact, but how you want to interpret that is up to you, of course.
I have a very much more basic question. In terms of you wanting to interpret the double scale SYK model from coming from this like q-deformed is coming from random matrix theory. You have an infinite sum there over B, but if I do out the like random matrix theory calculation and I look at what the trumpet contribution is, it's an integral over B. It's not an infinite sum over B.
Yeah, that's funny.
So why?
But actually, that's for double scaled matrix integrals, it's an integral. For finite cut matrix integrals, it's actually a sum.
Oh, okay. So you're saying this is, oh, okay, because when you do the, okay. I see. Thanks.
There's actually a funny, even like the math is extremely simple, like the difference between a double scaled matrix integral and a non-double scaled matrix integral is in the theta basis, it's like, or in the energy basis, it's like you do cosinus B times phi h of energy, 1, cosine B of phi h of energy 2. Then either you do integral dB, or you do sum over B. This will give the universal answer for a double scale matrix integral. This gives the universal answer for a single cut matrix integral. So really only the discretization of B. So yeah, I found it kind of surprising.
Perhaps I missed it. I asked earlier, you said you would answer patiently.
I think it was so interesting.
So you said that this thing works only with certain topologies. Can you explain later? So which topologies does it work for?
So I explained the topologies that I understand, and the other topologies I don't yet understand. So the topologies that it works for are cylinders, such as the trumpet and the double trumpet. And actually, the disk in our theory turns out to, in some sense, also be a cylinder because of this equation. The disk, in some sense, is also just a sum of cylinders.
So I can think the reason it works is because it's flat. I can think of it as being flat.
Yeah, or at least if I would I do the global shift of phi, then it gives like the other character, and if it's a cylinder topology.
But the
So
other
global
transformation now, if you have the cylinder, you can wind around it.
Yeah, so you have a winding motion or something. Whatever.
Yeah, but your action 5 times R, what are you going to do with the winding?
So maybe it's not the same because at the end of the day, you did this with the P, right?
Yeah,
The mechanics, so somehow.
but for the closed channel, it was more.
Either it's flat, either you can see a flat metric, but then you have to face the issue of winding. Right, it's the zero mode versus the winding. You either get one of them under control or the other.
Yes. I think what happens here typically is that the action actually is the sum over all the winding modes of the action of a given winding mode. So the action is not just e to the s, it's actually the sum over all these exponentials. This is typically how these q-deformed theories work. So
My problem is much more elementary. If phi winds around, there is no non-zero curvature. This has to be defined more carefully.
Right. But then if you define it as a sum, then if you go around and that phi one number, basically you're relabeling terms. And so your integrand can still be, in the path integral can still be periodic, even though the individual actions aren't.
If you're talking about shifting the zero mode.
The
Talking
issue
about
is that
shifting
should
to
be
zero,
single
I'm talking
value,
about the
not
one
this
with
saying
lines.
that it should be single value, the action, right? So it's not, even if we include this.
No, I wasn't saying it's not single value, just saying it's not defined.
Yeah. It's not well defined because if you pick a trivialization that
okay,
phi is
fine.
real, I pick another trivialization, we're going to get different answers.
But in the one,
Same,
instance-
maybe, yeah.
Are there more questions for now? If not, let's thank Andreas again.